Hi folks, this is Nat, and this is going to be your video lesson on calculating compound probability again. But this time we're going to be focusing on dependent events, which is different than last time when we talked about independent events. So the very first thing we're going to start off with is trying to understand the difference between independent and dependent events. Everything that we looked at last time was an independent event. And I think we said at the beginning of that when you think about an independent event, it's an event that doesn't affect or isn't affected by some previous event. You might think about this the way you think about independent generally speaking. If you think about an independent thinker, for example, it's somebody who thinks for themselves and doesn't get swayed by other people. Same idea. When an event is independent, it's not affected by other events. An example of this might be rolling a die. If I roll a die multiple times, the number I get on the first roll has no effect whatsoever on what I end up getting on the second roll. Getting a 6 on the first roll doesn't mean that I have any different probabilities of getting a 6 or anything else on the second roll. So those are independent events. A dependent event is the opposite. When you talk about a dependent event, one event does affect another. A great example of this is a deck of cards. When I draw a card from a deck, if I don't put it back, all my probabilities change because I've removed one of the cards. So there are fewer things that can happen and fewer of the outcome that I've removed. Let's take this simple example. Say I have just the cards 1, 2, 3, 4, and 5. It's a very small deck, but I'm going to draw a card from it. Right now, initially, the probability of drawing a 1 is just 1 in 5. But if I draw a card, let's say I draw a 5 out of here, the probability of drawing a 1 now changes. The probability of getting a 1 is now 1 in 4, not 1 in 5, because there are fewer cards left in the deck. So my probabilities are changing. They're affected by the fact that I've drawn a card out. And so these are dependent events. Just like with independent events, I can make charts and tables and figure out the number of different combinations of things that can happen with dependent events. For example, if I, again, have a deck of cards and it's numbered 1 to 7, I can figure out all the different combinations of 2 cards, or 3 cards even, that are possible to be pulled out of here. So what I'm going to do is say, if I want to know the number of combinations, how many cards are available to me to pull the first time? And the answer is going to be 7. I have 7 cards available on the first pull. Now we, though, have to imagine a missing card, and it doesn't matter which one. If I pulled a card out of the deck, there's not 7 anymore, there's 6. And so the second time I pull a card, I don't have 7 things to pull from, I have 6. Meaning that there are now only 42 possible combinations of different cards that I can pull. 7 times 6. 7 cards on the first pull, and 6 on the second because I've removed one. I can also diagram this out. And diagramming it out actually looks very similar to what you do if you wanted to know, well, what are the combinations if I pulled the cards 1 through 7 and put them back again, where I could have pulled the same thing twice. On my first pull, have the choices of pulling a 1, a 2, a 3, a 4, a 5, a 6, or a 7. And the same thing on my second pull. Generally speaking, I have the choice on the second pull of pulling a 1, a 2, a 3, a 4, a 5, a 6, or a 7. I might pull any one of those on my second pull, dependent on what I pulled on my first. The thing that isn't possible is to pull the same card twice. So when you make a chart or a tree diagram of dependent events like this, you're going to be eliminating things as you go. So for example, I can't pull the 1 more than once. So pulling 2 1s is not a possibility. I can't pull the 2 more than once, or the 3 more than once, or the 4, the 5, the 6, or the 7. So if we have 2 dependent events and we diagram them, we're typically going to be crossing out this diagonal, assuming we've organized our numbers well. Every other event on here is possible, and these account for all the 42 different combinations we could see. I could get a 1 and a 2, I could get a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, a 1 and a 7. I could get a 2 and a 1, but not a 2 and a 2. I could get a 2 and a 3, a 2 and a 4, a 2 and a 5, a 2 and a 6, a 2 and a 7. And I can keep going and fill out this whole chart. And then I can see essentially every combination that's available, all 42 that we discussed. I could also have diagrammed these combinations out with a tree diagram. I could have said on the first pull I have a choice of a 1, a 2, a 3, a 4, a 5, a 6, or a 7. Now, the tree diagram gets a little bit weird, and it's going to be kind of tight here, so I may not do the whole thing. But the tree diagram gets a little bit weird because then on the second pull I have to think what options are still available. If on my first pull I pulled a 1, well, a 1 is no longer an option, so I'll skip 1 on the second layer of my diagram. I could now pull a 2, a 3, a 4, a 5, a 6, or a 7. Since I don't have a ton of space, I'm not going to do all of these, but I'll show you the 5. If I had originally pulled a 5, I could now pull a 1, because that's still in there, a 2, a 3, a 4. I can't pull another 5, so I'll skip and say I can pull a 6 and a 7. So while my first thing had 7 options, each additional tree or each additional branch section that comes out is only going to have 6 extra options. So 7 initial options times 6 follow-up options, again, will give me 42 total choices. Here's an alternative version of this problem, or this type of problem. Say 6 people are running a race, and I've got a lovely drawing of 6 people here, and I want to know how many different ways can they come in first, second, and third. When I think of who can come in first, or better yet, how many people can come in first, well, there are 6 people running, so 6 people could have come in first. Now, let's just imagine this guy comes in first. So he's done with the race. Now I want to know who comes in second. Well, there's 5 remaining people who could still come in second. So 5 follow-up options after the first place to be second place. Well, after that second person comes in, now for third place, I have even fewer options. Only 4 people are available to come in third place. So my total number of combinations are going to be 6 times 5 times 4, which in this case is 120. There's 120 different ways that 6 people could finish in first, second, and third during a race. Now, diagramming this out is going to get really messy, and so I'm not going to even try to do the whole thing, but I'll show you how you could at least start it. Because there are 3 things happening, a first, a second, and a third place, I lose the ability to do a nice easy chart, so a tree diagram is really one of my only choices here. And you, again, just think about what can happen. Well, if I give these people numbers or letters, doesn't really matter. Person 1 could come in first, 2, 3, 4, 5, or person 6 could come in first. And that's the first layer of my tree diagram. From there, if I imagine that person 1 came in first, there's 5 remaining people who could have come in second. So person 1 could have come in first, person 2, 3, 4, 5, or 6 could have come in second. And it'll be the same thing for every other section, except if person 2 was the person coming in first, they won't be able to come in second. So for person 2, it could be person 1 is second, person 3, 4, 5, or 6. But you're going to see, again, in that second layer, for every person that came in first, there's 5 options of who then could have come in second. When you get down to your third layer, it gets a little trickier still. So let's say person 1 came in first, person 2 came in second. Now there are 4 remaining people who could have come in third, and that could have been person 3, 4, 5, or 6. If person 1 came in first and person 3 came in second, the Third place people could be person 2, person 4, person 5, or person 6, and so on. And you can see I'm going to get to a pretty gigantic, unmanageable tree diagram here, and that's because, again, there are 120 different possibilities based on my math that I did over here. 6 options for who came in first, 5 for who came in second, and 4 for who came in third. But this is another great example of dependent events, or dependent combinations of events. Because the winner, the first place winner, affects who can be second, and the second place winner affects who can be third. Because of how complex these things can get, it's really nice that we can actually rely more on calculating dependent probabilities, because they're not much harder to calculate than independent probabilities, and it reduces our workload a lot. We don't end up with a huge diagram. And the other thing that's nice is the probability of A then B happening is still going to be equal to the probability of A times the probability of B. So that hasn't changed. The only difference is that as we calculate our different probabilities, we have to account for the changes happening and one being dependent on the other. Let's use as an example this fake deck of cards here. I'm going to point out to you that there's a little bit of oddness in here. I've got a 1, a 2, but 2 3s. 1 4, 1 5, and 2 6s, so the probability of every number is not exactly the same. I could start by thinking about combinations in terms of how many different 2-card combinations might there be. If I were to pull 2 cards, on the first pull there would be 1, 2, 3, 4, 5, 6, 7, 8 different cards that I could pull. So on the first pull, 8 possible cards. But if we imagine that I've taken one, on the second pull there'll only be 7 possible cards, meaning that there's only 56, not 64 combinations. I could diagram that out if I wanted to, but I'm not going to right now. Let's say that what I want to do is calculate my probability of getting 2 3s, a 3 then another 3. Well, the probability of my first 3 is actually not too hard to calculate because I just have to look at it and say, okay, there's 2 3s out of 8 cards, meaning that there's a 1/4 probability of pulling that first 3. The second 3 is different, and here's what I have to do. I have to imagine that I've successfully pulled one of those 2 3s and think about how the probability has changed. With 1 3 gone that I've pulled presumably on the first pull, there's now only 1 3 remaining out of 7 cards, meaning that the probability of the second 3 is only 1/7. Then still means to multiply together, and so the overall probability of pulling both 3s is going to be 1/28. 1 out of 28 times I should pull both 3s. Here's another example. Let's say I want the probability of a 3 then a 6. The probability of the 3, again, is 1/4 initially because there's 2 3s out of 8 things. So I have a 1/4 probability of getting that 3. And now I'm going to imagine one of those 3s is gone. The probability of the 6 is going to be 2 6s out of 7 remaining cards. Again, keeping in mind I don't have 8 cards anymore. I imagine I pulled one. So the 6 has a 2/7 probability of being pulled. Then means multiply. So I'm going to multiply these together. 2 28ths reduces to 1/14, and that's the probability of pulling a 3 then a 6. Just as a quick example of how quickly this can become super complicated, let's say I want the probability of a 3 and a 4, but in any order. It's going to be worth rewriting that as the probability of getting first a 3, then a 4, or getting first a 4, then a 3. So this is a compound probability. The probability of a 3 is still 1/4 if I pull it first, but the probability of that 4 is going to be 1/7 because of the missing 3 I'm assuming is gone. I'm going to add that to the probability of a 4 then a 3. The probability if I pull a 4 first is 1/8 because originally there'd be 1/4 out of 8 cards, but then the 3 would be 2 3s remaining out of 7 cards. If I simplified that big expression, I'd have the probability of getting a 3 and a 4 in any order. It would end up being 1/14. And here are your practice problems. These have to do with pulling blocks out of a bag without returning the first, so your options will change as you go. Good luck.